All right. Let's start. Good afternoon. So a couple announcements. Homework 1 has been graded, so you should be able to access the comments of the TAs on Blackboard. Homework 2 has been posted. It's week 1 week from today. Okay. And we have our first midterm in October 10th. I had a mistake in my syllabus. For some reason, I think I have October 11th, which is not a Tuesday. So it has to be Tuesday, okay? And so for the remote students, if you're not planning to come to campus for the midterm, it's very important that you submit your proctor forms as soon as possible so it can be approved, so I can send the exam to your location. Okay? And finally, I usually have office hours after class. Instead of being in my office, I'm going to be at the lab in Hayden, in the basement, so if you need to talk to me, please come over there. Okay? Any questions on anything?
When's Project 1?
It is due 2 weeks from when it was given, which was last Friday, so it's 2 weeks from, 1 week from Friday. Okay. All right. So the plan for today is to finish edge detection. So last time I introduced to you the idea of finding local gradients. We saw a way of doing that. We saw that if we don't do if we just take differences to approximate the derivative, what happens is that we increase the noise variance. So when we do edge filtering, we do two things together. We do noise cleaning and we do also edge detection. So we're going to go a little bit over that just to make sure that everybody remembers. And then we're going to move on to Canny edge detector, which is the most commonly used detector in the literature. So any paper that starts doing edge detection, the first thing that you would read is that it's using a Canny edge detector. And there are good reasons for doing that. We're going to talk about that. We're going to talk also about other edge detectors, the Laplacian, which is not so commonly used, but still is worth knowing about it. And then I'm going to talk a little more of what has happened in the recent years, in like the 3 or 4 years ago, where people have been trying to actually use machine learning to do edge detection. So it's more at the semantic level rather than at the very localized level of the pixel level. Okay? All right. Okay, so this is what we did last time. We said we're looking for places where the image values change drastically in a very short space. Okay, so we're looking at things that go from, say, low to high, but it could be also from high to low, of course. Okay, and we saw that one way of doing that was to take the signal and take the derivative of that and look for the gradient. Now, this is in 1D. Our images are in 2D. So what we want is to be able to find lines like that again, they're separated in 2 regions, one region being darker than the other. Okay? So in 1D, we did the derivative. In 2D, what we had to do is work in 2 dimensions. So the equivalent of the derivative is the gradient. And the gradient is a vector. It has 2 components. And that's good because that gives us important information about that edge that we're looking for. It gives us the magnitude of the vector that has to do with how big the jump was. Okay? How much was that difference between dark and bright? And it gives us also the orientation, so we can know the orientation of the line or the edge of the boundary at that place, which is orthogonal to the gradient vector. Okay? So we find that it was in 1D, we say that there is an edge if the value of the derivative, the magnitude of the derivative, the absolute value, I should be having an absolute value here, is greater than a threshold. And in the gradient vector, what we do is we compute the magnitude. And sometimes we compute the Euclidean magnitude, so it's the 2D norm, so the sum of the squares, the square root. Okay? Sometimes we are in a rush, and instead of doing this, what we do is sum the absolute values of each component, and that also works. Okay? And as I said, it also gives the orientation. So the tangent of the angle of this vector, which is perpendicular to the edge, is given by the ratio of the two components. And depending on who is your reference, the horizontal or the vertical axis, you might see the first component divided the second component or vice versa. It's just a matter of which axis you pick as your reference for the angles. Okay? And as long as you're consistent, you're fine. Make sense? Okay. All right. So we also discussed the nice property of combining the smoothing with the edge detection, right? So we saw that if you have a noisy signal, right, we should first clean it up and then apply my edge detector to it to find where the edge is, because otherwise the noise could overcome the edge and I wouldn't be able to see it. Okay, and we saw that instead of doing this in two stages, first cleaning and then doing edge detection, we actually can use the linearity of the operator of the derivative and the convolution and combine them together into a single operator. Okay, and so we should take the original signal and now we convolve with this filter. In this case is the derivative of a Gaussian, but it could have been the derivative of a box filter. Okay, so it depends what you use to smooth out. And you get your edge detection. Okay, and then we saw a couple of masks. This is a pre-width mask. This one is finding vertical lines. Okay, and it has 3 rows. And again, the 3 rows is an effort to take care of the noise, because what we're doing is smoothing out in the perpendicular direction to what we do. So we take the differences along the horizontal direction, and then we average along the vertical direction. Okay, so we are combining noise cleaning and edge detection in one mask. This is for the vertical ones. We have a similar one for the horizontal ones. And we also saw the Sobel operators, which they're basically the same as a pre-width, but they give more weight to the 4 neighbors instead of having all the neighbors on the left and right or top and bottom to have the same weight. Okay? Yes? All right. Okay. So let me now talk about the CAN edge detector. As I mentioned earlier, it is one of the most popularly used edge detectors, and it was derived using first principles in signal processing. We're not going to go through the details. It's beyond the scope of this class. You need to know a little more of signal processing that I want you to have as a requirement. But I'm going to tell you a cartoon story of how CANI came about this. Okay? So he thought about this in the terms of that when you do edge detection, there are really 3 steps involved. Okay? The first step is that we need to deal with noise. We saw that taking derivatives is bad because of the noise. Okay? The second thing is you need to find a way of lifting up the signal at the edge location so you can detect it. Okay? So that's edge enhancement. And then you want to have good localization. You want the edge to happen, to be found where it's actually happening and not shifted to the right or to the left or okay? So he wanted to address these 3 things. Okay? And he did it in a way to formalize a problem where he had a theoretical model of what an ideal edge was, how that edge was corrupted by noise, and how to try to have good properties in terms of detection and localization. Okay. So it works well. It's very popular. Okay. And as I said, it uses a mathematical model for the signal and the noise. And the model is very simple, actually. What you assume is that the edges, ideally, if there was no noise, we had been a step. Okay. Actually, in his paper, he discussed more than just a step edge. He has also ramp edges, and he has roof edges, and so forth. But for this class, just think about step. Okay, so and he formalized a criteria that he wants the detector to satisfy, so hoping to have good results. Okay, and the paper starts very nicely with setting up all of these in equations, and at some point says, well, if these were my equations, I could solve what the optimal filter was. But then he asked one more constraint that he would like to have, and unfortunately in that case it becomes not solvable in a closed form solution, so he did it numerically. So he actually synthesized the optimal filter to satisfy this. Okay, and I'm going to show you in a minute what that filter looks like. Okay, so let's work in 1D, the same way that we did with the simple mass that we talked about last class. We can start with 1D and then expand it to 2D. So in 1D, we have the model as a step, and we're going to assume that the step happens at x equals 0. Okay? So this is the model of my ideal edge. On one side is dark, on the other side is bright. The amount of jump is A, and it's instantaneously. Okay? It happens just in a vertical jump. Okay, so this function g that models my edge is 0 if x is negative, and it's A if x is positive. That was his model for the ideal edge. Okay, and then on top of that, he added noise, and not surprisingly, he thought about having additive white Gaussian noise. Okay, that's what it would do. Okay, and that's characterized by the signal-to-noise ratio between the edge and the noise. Okay, and so we have some variance in zero square. Okay, and this is actually one of his main contributions was in how to formalize what makes a good edge detector. Okay, and so he said, I want good detection, I want good localization, and I want low false positives. All of this seems like, apple pie, right? That's what anybody would like. So what he did is he took these words of nice properties and convert those into mathematical terms. What do I want to do my filter to do? Okay, and so for good detection, what it means is that if I have an input signal that might be noise, is an edge plus noise, and I pass it through my filter, what I need to come out on the other side is something that is amplifying the signal at the edge location and not everywhere else. So I want to enhance where my edges happen. Okay, so my filter should be doing that. And by the way, he was looking for a linear filter. Okay, the second thing is he wanted a good localization. What that means is that this nice peak that you have over here, you really want it to be around x equals 0, where it is my ideal edge. Okay, so I want to find the edge where it happens. Okay, so I want to have a large peak on the output, and that peak has to be near x equals 0. Okay, and again, if he did this too, and he did this in a nice, way of working with the frequency response of the filter, he actually can solve for the closed form solution of what is the best filter that satisfies this. Okay, but then he added one more constraint. The more constraint was the third one. He said, I want to have low false positives. What that meant was that my signal, after coming out of the filter, might have more than one big bump. Okay? But I want these other bumps not only to be small, but also to be far away from my edge so I don't confuse them. Okay? I really want to have this guy. I don't want to have this guy. So I want this distance between the largest peak and the next peak to be large. Okay? And when he added this constraint, unfortunately, the nice math went away. He couldn't actually solve it anymore in a closed form solution. Okay? But he did simulations, so he found numerically what was the best filter. Okay? That satisfied these three constraints, and it was a linear filter. Can you guess how that filter looked like? No? You actually have already seen it. Okay? What it looked like is the first order derivative of the Gaussian. Okay? And so what it's doing is doing a difference. So you have a positive lobe and a negative lobe. Right? So you are, when you're convolving with that, you are computing differences. But the Gaussian part of it is also taking care of the noise. Okay? And so, again, this is not the optimal solution of the problem that he formalized, but it's a very close to what the actual real solution is. Okay, so this is the basics of the canny edge detector, but it's not the only thing about the canny edge detector. Okay, so he addressed, as I had in my first slide, three things, okay? He wanted to have good detection, right? He wanted to have good localization, okay? And so, and low false positive. So he did this thing. Okay, sorry, this is saying what I said before. That combines again, okay? So the edge detector with Canny has actually 3 steps. In the first step, we're going to enhance the signal. On the second step, we are going to thin our edges so they're well localized. And in the third step, we're going to do thresholding to actually detect, okay? And he made contributions on all 3 things, all right? So here is the first part, what we call the enhancement of Canny, okay? And so I have an input image I, and I'm going to, and this is a conceptual Canny edge detector because it's not the most efficient implementation of it, okay? I have a Gaussian zero mean filter that I'm going to use to smooth my noise, okay? So, and this Gaussian filter has a parameter sigma, right? So that means how much I smooth in my signal. If sigma is large, I'm going to blur more my edges. If sigma is small, I'm going to blur them less, okay? All right, so the first step is, again, this is not the optimal way of doing Canny, but conceptually, you would take your image and you smooth it out with a Gaussian filter. That gives you a new image J. And then for each pixel, what we're going to do now is enhancement. So this was the smoothing, and now I'm going to do the enhancement. And the enhancement is taking the derivatives, and in discrete signals, what we're going to do is take differences. So what we're going to do is compute the image gradient with our favorite mask, 3x3, for example, or 2x2, or 1x3, with the differences, okay, on the left and the right, on the top and the bottom, okay? So now I have 2 images, one for the first component of the gradient and one for the second component of the gradient, okay? And then I'm going to estimate the strength by computing the magnitude at every pixel, and that will give me another image, which we're going to call ES for strength, okay? And this has just the square root of the sum of the squares of the 2 components. And also, we're going to estimate the orientation of the edges by using arctangent of the ratio of the 2 components, okay? So I started with image I, and now I end up with 2 images, ES and EO. ES has the strength of the gradient, and EO has the orientation of the gradient, okay? And so I'm going to output this, and this will be the output of my first step, all right? Now, why I'm not done? I'm not done because my edges, if I do this, will be thick, okay? Let's see how that can happen, okay? So I have, this is, again, I'm doing in 1D. This is the profile of the output, right? And I'm going to try to detect an edge. How do I detect an edge over here? What I need to do is to find local maxima. I need to find peaks, right? How do I find peaks?
First order derivative.
No, I already have, this is my first order derivative. If I do another derivative again, I end up in the Laplacian. We will do that later. But now, this, I'm processing this, and I want to find my peaks. What do I do?
I think use a high pass filter, only like the high value.
I can use a threshold, right? I say anything that's higher than something is high enough, I have an edge, right? So I need to pick a threshold, okay? Pick a threshold. Anything above that threshold, bless you, is an edge, okay? So here I pick my threshold high enough that I don't have these bumps, and low enough that I keep this guy, right? Now I'm saying that my edge, bless you, that my edge is going to be thick. Why is that? Why do I say that?
Because if you look, it's not like you don't have one point, it's the width of your spike.
Right. And remember, this I painted continuous, but I have a grid, right? So my thing looks like that. And these are the points that I'm looking at, right? And when I put my threshold, I'm picking 3 guys, not just 1. Okay? So it could have been fat, but it could be within the grid. But here I'm making it fat and covering more than 1 pixel. Okay? So I want to avoid this. I want to clean this up. Okay? So the next step is what's called non-maxima suppression. And the non-maxima suppression, what it will try to do is to thin my edges. Okay? How do we do that?
Can you take the median point?
Yeah, that would be one way. No, that's not the way he did it, but yeah. Okay. So now what we're going to do, it's similar, as you're going to see. What we're going to do is we're going to traverse along the direction that's perpendicular to the edge, right? Along the vector of the gradient. And we're going to look at my neighbors in that direction. And I'm only to pick the guy that's the tallest guy. Okay, so if I am shorter than my neighbor, I say I'm not an edge, and I become 0. Okay, and the idea is that I pick my local maximum over that. Okay, which is cheaper than sorting. Okay, so here is the algorithm. Okay, non-max suppression. It takes as input both the strength of the edges and the orientation of the edges. Why do I need orientations? I'm going to do the non-max suppression along the direction which is perpendicular to the edge, okay, to the boundary, and so I need to know that orientation. Okay, so one way to do this is first I discretize the possible orientations. Of course, when I do the tangent of theta, I can have any angle, right? But we're going to do in discrete intervals because we're going to move on the image along either north, northeast, east, southeast, or south. Okay, so I have a discrete way of moving on the image. And then for every pixel, what I do is I find the orientation of the edge, which of these directions on my compass is the closest one. And that tells me how I need to walk to look at my neighbors. And now I check whether I am the tallest one or there's somebody that's smaller than me. Okay, so if there is somebody that is smaller than at least one of his neighbors along that D, then that guy will become 0. So this is the output at that location in the case that there's somebody taller than the pixel. Otherwise, we keep the strength. Okay, so what we're doing is we're taking the strength image, and some of the pixels become 0. Okay, which becomes 0, the ones that are nearby another guy that's much taller than them. Okay, that's the main idea. And so that gives us the thin edge image. All right. So here's a graphical interpretation of what I did now in 2D. So I have these 2 regions, but in the middle this has this gray area, which is sort of a combination of the 2. If I did edge detection, I will find the gradient perpendicular here. And now I will go and walk along this direction. I look at these guys, and I see that this guy is shorter than this guy, and so that will get removed. This guy is shorter than this guy, so that will get removed. Okay, and so in the end, I only have 1 pick. Okay. Am I done? So I did 2 steps. I did edge advancement, right, that clean noise and find the gradients. And now I did non-max suppression to thin my edges. Okay? Do I know where edges are? Not yet. What do I need to do? The final step. No, the orientation was given here, right? This guy remains. So whenever I have something that is non-zero on the output of this guy, I look at the orientation, I have the orientation. So I have the places where I think there are edges, right? I know that they might be thin, okay, and I have the orientation. So, but how do I really localize? Again, what I need to do is the thresholding. Okay, I need now to pick my threshold. Okay, yes.
How do you know it? Would you have to find 2 points within that edge to know that it's like a line?
No, so I go along, this is D, this is so I have the gradient vector, this is the gradient vector. That gradient vector has an orientation. So now I move along that direction, and for each pixel, I look to my left and my right in that direction, and see if anybody is smaller, taller than me.
Right, but then you're only looking at it within like a ring, like.
But you do that for every edge.
Oh, okay.
You do it at every location. You do that. Okay. And you do it in a small neighborhood, right? I don't walk miles on the image. Yeah. Okay. All right. So now I need to find the threshold. Okay. And finding thresholds is, I'm going to do that after doing the non-max expression. So I'm going to have that output as non-max expression. I'm going to threshold that. But finding the good threshold is tricky. Okay, it's kind of an art. Okay, why is that? What happens if I find a threshold that is too high? If the threshold is too high, right? Even the tallest peak is below my threshold, so I have no edges, right? And maybe it was not so high, but still it might be too high, and I miss a lot of edges. Okay, so I have misdetections. Okay, what happens if the threshold is too low?
You get noise. Well, you'll see noise as edges.
If everything becomes an edge, right? Potentially everything that survived the non-max suppression would say an edge. So I have a lot of noise in it. Okay, so I have a lot of false positives. All right, so I need a balance between that. Okay, and it's a tricky. There are actually algorithms to try to find this in an automatic way, but still it's an open problem. Okay, now what Canny proposed in his paper was to have 2 thresholds, not just one. And he proposed that strong edges help boosting up weaker edges. Okay? Let me try to explain what that means. Okay? Suppose I have this contour over here that was after doing the non-max suppression. So the fact that this guy is thicker than this guy is not that I have a thicker boundary. What it's trying to represent that in these places, the strength was higher. Okay, so I'm representing a strength now with the thickness of the line. Okay, so over here it was very strong, really strong edge. Okay, over here so-so. And then this should have been a close shape, but what happened is that over here the strength is very low. Okay, still there, but very low. All right, so the strong guy over here and this guy over here, which is medium strength, they all satisfy that they are in strength greater than a high value threshold. Okay, so they're high enough that if I pick a threshold H for high, they will survive. They will become edges. Okay? Now, this guy over here is less than H, so I will lose that. Okay? So instead of having my closed thing, I will have the gap. So you say, well, maybe H is too high. Let's lower H. Okay? So now I use a threshold L for low. Okay? And this guy will survive that thresholding, but bummer, this guy here, which is noise for me, I don't care about it, also survives that. Okay? So if I pick L, I pick my whole contour, but I also pick this S here. If I pick H, I pick the thick ones, but I miss this guy. I miss the noise, which is good, but I also miss this guy. Okay? So he wanted to have both. Okay? So what he said is, let's first pick strong edges. And then look next to me. If next to a strong edge there is a so-so edge, let's bring it over because it's my neighbor and I believe probably is connected to me. But this guy is isolated, so, and doesn't have any strong friends, right? So then it will be discarded. Okay, and that's what's called hysteresis thresholding. Okay. So here is the algorithm. The input is the output of the non-max suppression, and the output will be and also we have the orientation that came up from the Canyon answer. And we will have two thresholds. And again, still, you know, if it was hard to pick one threshold, it's still hard to pick two or more, or even harder, right? But the idea is that if you pick them right, you can do better than just with one. Okay. So for every pixel in the image, what we do is we scan the image in a fixed order, for example, from top to bottom, left to right. Okay. And we find the first pixel that we had not been there and see if it's strong enough to be picked as a strong edge. Okay, and that is like the end of a string that I'm going to start walking along, right? And I will walk along as long as I am at least higher than the lowest threshold, right? Okay, so starting there, I make this local chain that goes from one pixel to its neighbor using a fork-connected path or a net-connected path. I had to decide that. Okay, and as long as that neighbor is greater than the lowest threshold, I will pick it up. Okay, and when I run out of that thing, I follow my scanning until I find a place that I have not been before. Okay, so very simple. And so what is nice about this is that not only doing edge detection, but actually doing boundary detection, because it's connecting these edges into chains. Okay, so you're getting a little more than just an edge detector. All right, questions? No? Okay, so this is the picture how I did it. So I scan from the top to the bottom, left to right. I find the first unvisited guy is greater than the threshold, so I keep walking around it. And this guy is less than the threshold, but it's greater than the low, so it will pick it up, and so on. Okay? All right, so that's the end of first order edge detectors. I promise I'm going to talk about some other edge detectors. We're going first to go to the second order edge detectors, and then we're going to move on to, as I promised, the semantic edge detectors. Okay? So second order derivative filters, what it does is something, I forgot who was, but somebody here said take the derivative of the derivative, right, to find the peak. And that's exactly what it is, right? So I took my first order derivative, and now my edges happen at peaks. I want to find the peaks, so now what I'm going to do is find maximum. So what I do is take the derivative and set that derivative now to 0. Okay? Before I was looking for high values of the derivative. That was where the edges happen. Now if I do a second order derivative, I'm looking for a derivative equal to 0. Okay? All right, so here's the picture. This was a cartoon of an edge in 1D. This is the first order derivative. I have this peak over here. If I take the second order derivative, now it will look something like that. Yes? Okay. So I have two lobes. Over here is positive, over here is negative. This has to do with the concavity of how I draw my edge, right? So here I have positive concavity, and here I have negative concavity, right? And the edge happens right there, right? So what I need to do is look for places where the second order derivative is equal to 0. Is that right? It's a tricky question. Why is might not be totally right? No, yeah, we deal with noise, but
Can there be multiple zeros as well? You need to check it.
right. I'm looking for edges. Keep that in mind, right? So if the second derivative is 0, it could be something like this. But also, if my function was constant to begin with, no edge. Right? First order derivative is equal to? Second order derivative is equal to? 0. Right? So if I just look plainly for zeros, yeah, I'll find my edges, but I also will find places where there are no edge at all. Okay, how do I tweak this then? What do I need to say? I need to find, yeah, or look at this picture.
Neighbors should be non-zeros.
So it first was positive and then went negative. So what the zero is, what we call is a zero crossing. So it's changing sign. It's going from negative to positive, in this case because I went from dark to bright, or from positive to negative, it was the other way. Okay? So what really I'm looking at is not places that are just plainly zero, but places where the derivative is changing sign. That's where the peaks on the first order derivative are. And that's where the edges are in the given image. Okay? All right. So this is what I just said here. Into D, how do we do this? What's the equivalent of second order derivative in 2 dimensions? The equivalent was, the first was a gradient. For the second was?
I was going to say that a second order partial derivative.
Right, and I'm sorry? Close, yes. It's the Laplacian, right? So the Laplacian is the sum of the second order derivatives. Okay, so let me, here I remember to put my absolute values. So this is in 1D for the first order derivative. In 2D, we have the magnitude of the gradient. In 1D, we take the derivative again, so the second order derivative, and we're looking for zero crossings, not just zeros. Over here, what we're going to do is look for zero crossings of the Laplacian. Okay? All right. So again, the Laplacian is the sum of the second order partial derivatives with respect to x and y. Can anybody tell me a big difference between this guy and this guy, besides saying first order and second order? What else is a big difference between the two? Nobody? I'm sorry?
You don't take the magnitude.
Well, yeah, I mean, this is a vector, right? So we were talking about the magnitude of the vector. It has two components, one in the x direction, one in the y direction. The Laplacian combines those directions into one scalar. Okay, it takes the first order derivative of each component and then sum them up. Okay, so over here I have two things, either the x and y component or I have the magnitude and the orientation, but I had to have two things to represent. Over here now I have just a single scalar. Okay, is that good or bad? I lose my orientation, so that's bad. Is anything good about it? Computationally simpler. Why?
You don't have to calculate.
I don't need to have two masks. I can do this in only one mask. Okay? In fact, I don't have to go through the first order derivative and do it again. I can do, all of these are linear operators, so I can do it with just one single mask. Okay? So computationally speaking, it's faster. Okay? But now we have lost the orientation. The other thing is that if taking first order derivative was bad for noise, taking twice is even worse. Okay, so you really have to be careful with your noise when you're applying a second order edge detector. Okay, and that's why you typically don't see it done in isolation. You do combine it with noise cleaning. Okay. All right, so how we do this? Well, we first we could do this. First, smooth with a filter. We can pick box or Gaussian. Let's pick Gaussian. Okay. And then I do find the zero crossings of the convolution of the filter image with using the Laplacian mask. Okay, so I have the image filtered with a Gaussian filter. The result, I get the Laplacian. Or, again, I can use linearity, right? And instead of doing two operations, I can combine noise cleaning with the second order derivatives, right? And what that means is that now I convolve my given image with the Laplacian of the Gaussian. Okay, and that's actually the name of an edge detector, the Laplacian of the Gaussian, or log. Okay, and here's how it looks like in 1D. So we start with a Gaussian. That's that. Then we take the first order derivative. It looks like this. Again, it's like the Canny edge detector. And then I'm going to do it here again. This is that. And now we take the second order derivative of that. Sorry, the first order derivative of that, so the second of the original one. And I get something that looks like that. And if I plot it, it looks something like this. Okay? Now this is in 1D. All right? We want to do this in 2D. So what we're going to do is we're going to take this guy and spin it around the vertical axis. And how does it look like when we do that? A Mexican hat. Okay? And that's why it's called the Mexican hat edge detector. All right? And again, this will do fine edges. We lost the orientation. We had to do something else for that. Okay? But you do in one shot, you look for zero crossings. And the nice thing is, well, what happens if you don't, when you apply this, you don't find a zero crossing, but you have a pixel that's positive, and the pixel next to that guy is negative. What can you say? Do I have a zero crossing? Yes. Okay, and you can interpolate and figure out where it is. So you can get sub-pixel accuracy where that edge is happening. Not the orientation, but the location. Okay? You have a question?
Yeah, I was going to I think you mentioned it before, but what's the advantage of knowing the orientation?
I'm sorry?
Well, what's the advantage of knowing the orientation?
Chaining, for example, right? So if I want to chain one edge to the next, I want to continue having it. So, yeah. Sometimes I don't use it, but sometimes it can be handy. Yeah. Again, once I know that there's an edge, I can go and try to find the orientation using the gradient. I can also combine that. Okay. Now the other thing is I mentioned, and the same thing happens with the Canny edge detector. One parameter of these edge detectors is the sigma used in the smoothing. Okay. So you can change the effect of your edge detection based on this sigma. Okay. So the example I like to give about this to try to understand is, suppose that my image is an image of a zebra. Okay. And I start applying Gaussian filter. Right? Depending on how big sigma is, I will get the stripes of the zebra. But if the sigma is too large, the stripes of the zebra are going to start merging with each other. And now I have a horse. Okay? So you could actually apply these kind of filters, the Canny edge detector and the Laplacian, by varying the sigma. And you can have multiple outputs and try to combine them. So you have a richer description of what the image looks like. Okay? All right. Let's move to this century. So let me talk about now something that is much more recent for edge detection. And this already is, I mean, now computer vision is moving really fast. So this is already a few years old, and they are even more modern than this. But I think this exemplifies what is happening in the field. Okay. So this is work by Piotr Dolar and Sitnik when they were both at Microsoft. Since then, they have moved. I think he's in Facebook now. I don't remember. Anyway, They do have code, and the title of the paper was presented in one of the main computer vision conferences in 2013, the International Conference on Computer Vision, and the title of the paper was "A Structured Forest for Fast Edge Detection." Okay? All right. So here's the tasks that they wanted to do. So I give you an image. I don't know why I like cows in this class, but anyway, I give you an image, and I ask, find the cows in the image. All right? So you apply canny edge detector, right? You say, I told how most people use canny edge detector. It's one very good principled design, and it has all these 3 steps that we saw, blah, 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 blah. Right? And this is how it looks like. Okay? So this is the image gradients and non-max oppression. So now my edges are thin. Okay? And these are doing some hysteresis thresholding. So these are the edges that show up. Okay? And now I ask, where are the cows? Do I have cows there? Okay? And what you see, of course, is that, well, this cow in the back is missing the top, right? Entirely. It's all missed, even with the hysteresis thresholding. And then I have these things, I got a lot of edges over here of these leaves that really are not what I am interested in this picture. Okay? Those are kind of background noise for my task. Okay? So clearly, canny is not paying attention to the meaning, the semantics of the edges. It's just looking very narrowly, very locally at a neighborhood and seeing whether there is high contrast between one side and the other side. That's all it's doing. Okay? So what these guys did was, well, I really want to do object recognition. I want to do object detection in these images. So I really want edges that mean something to me, not to the computer. Okay? So what did they do? Well, they actually recruited a lot of people. They didn't. It was already done for them before. But to annotate what edges are important. Okay? There's a lot of work, okay? But it has been done, okay? And so given images like this, humans went along and marked what's important to me, what I think matters in this image as edges, okay? So this is how the annotation, I hope you can see it in green, around the bear and maybe some of the foreground over here. And here the bears and the coastline and on the river, right? And so this is how it looks like. And of course, different people have different interpretations of what's important. So these databases, what they did is they have many annotators, and they kind of try to average or learn how variations are. But the idea is that there is this data set. In fact, since then, there have been more expanded data set. This was originally created by Jitendra Malik's group at Berkeley, okay, and it was again to try to benchmark segmentation algorithms. The idea was we will use these for ground truthing, right? So you apply your favorite edge detector, canny or a variation of it, you find the edges, and now you compare that against the ground truth and see how many you pick right and how many you are off. Okay, but obviously, I mean, these are again semantic edges in the sense that the annotators didn't bother marking all these extra branches over here, for example, or this over here in rocks in the river. While canny probably will pick those, right? So these are more what is meaningful. Okay, and then the answer was clear, right? This is the era of machine learning. So I have training data now. Let's train some algorithm that uses this annotated data as exemplars of what is an edge that I like, and then apply it to my images. Okay? So we're going to talk more about classification later on when we talk about object recognition. So here is a very superficial description of what's happening, but the idea is that you want a classifier. Okay, so you have samples. Okay, these, for example, might be samples of local patches around an edge that matters to me, and these might be samples of places where edges do not matter to me. Okay, so I have a positive class and a negative class. Okay, so I have a lot of these samples because a lot of people did this, and I have many images, and images have a lot of these little regions, and I train a classifier with that. Okay, so then next I give a region of my image, and the question is that an edge or not? An edge that I care or not? A semantic edge. Okay, and the answer lies on this classifier. This classifier becomes like an oracle that you give a sample and now picks a winner. Okay, because sort of learns a boundary between these classes. And the idea is that anything on one side of the boundary belongs to one class, anything on the other side of the boundary belongs to the other class. Okay? So there are many ways of doing this classifier. In this paper, they actually use a random forest tree, okay, which is one particular way of doing classifiers. One of the nice things was that they actually could do this in real time. So you actually could pass the image, and in real time you will get your semantic edges. So very clever implementation. In fact, Pietro Dollar has a toolbox for image vision and computer vision that I highly recommend to download to your machines, because he's really good programming, okay, and he has really nice code for doing things. Anyway, they train a classifier, and then based on a neighborhood, they give a score and decided whether there was. So here's again the example of a training image, okay. And so the samples that are labeled are like this. So you get patches in the image, and again, you can have patches anywhere. And if the patch has an edge, it's a positive example. If the patch doesn't have a label edge, it's a negative example. Okay? And then you take that patch, either positive or negative. This is a matrix. You can vectorize it. Okay, and that becomes your feature vector. Okay, or you can do even smarter things. In fact, they did. Instead of just taking directly the RGB values, what you can do is apply canny or other edges, gradients, and so now you have a richer feature vector that's picking up on the things that I'm actually looking for. Okay, so then you train your classifier now with this extra feature long vector. Again, you pick your favorite classifiers, support vector machine, or decision trees, deep learning these days, okay? And you get then that given a image like this, now I want to find where are the important edges. And so what you do is you take a window and you scan it, and you pass it through your classifier, and you say edge or no edge, or how much I believe that there is an edge over here or not. And so then you create an image where you put the score of the window, okay? And this is the kind of things that you get, okay? So this is the original image. This is if you apply gradients. This is gradient plus non-maximum suppression. So this canny type edge detector, and this is the edginess score, and it's very hard to see in this light. Is it better? Okay, it's in the slide, so you can see it in Blackboard, but the edges really do capture what is important in the scene, which is the car, and the horizon line over here, and the post. Okay, so these are things that probably a human would have marked as important edges in this image. Yes?
Does the size of the patch matter?
Yes, yes. There's a lot of tuning involved in this, right?
Is it more accurate if I use this smaller patch?
So no, it depends on the scale of the image. And when they did training, what they did is actually use the database, and they also scale it up and scale it down. So they have multiple samples at different scales. Okay, yes. So here is this region over here. This is what the image gradient looks like, and this is the edginess score. So here basically you see nothing, right? Because there's nothing really important in the scene. Okay, here's the cows, Okay, again, this is the edginess score, and this is using non-max suppression after that. This is an image again. This is the gradients and the non-max suppression. This is the score. This is non-max suppression. And going back to your question, well, again, depends on how you train. So if you don't include a small detail in the training data, you will not get it out of this segmentation, right? So for example, if you look at this trash can, it has letters in it, right? Can you read what it says? It says brute, okay? Now, if you apply that, if you look at the image gradients on the trash can, on the output of a Canny, you can see the letters. I still can read brute over there. But if I look at the edginess score around that area, the letters disappear. Okay? Why is that? Well, because again, when people label these images, they thought that that was a minor detail that was not important, and so it's not being picked up as an important edge. If it was important to you, if you were doing, sign recognition of stores for deciding, what store to go for a coffee or something, then you would pay more attention to that, and you would put that into your training data. Okay, so this is more of a methodology than the actual detector, although, again, their implementation is strikingly fast and nice. It does, they have really nice live demos where they do the edge detection in real time. Okay, questions? Okay, now, how to evaluate the performance of these edge detectors? How do we know they're doing a good job? Okay, and this is true not just for the semantic edge detector, it's also true for the Canny, the Sobel, and Prewitt, and so forth. Okay, so what you can do is look for statistics of how well you're doing. Okay, and over here I have a set of images. Okay, these actually are images that they have both color and depth. They were taken with a Kinect 2, so you have information not only of the color of the surfaces, but also how far they are from the sensor. And as you can imagine, that's helpful to segment indoor scenes like this, because now you can know that the bed is flat, right? And the wall is vertical. Okay, so you can do that kind of segmentation. So this is the ground truth segmentation of these indoor scenes. And these are the segmentation done with the semantic edge detector I just described. Okay, and so here are the scores. Okay, and then over here, the same guy had been painted depending on whether they agree with the ground truth, they did not agree with the ground truth, or they were missing. Right? So we have green is correct, blue is wrong, red is missing. So green plus blue is really what the edge detector output, right? The red ones, they did not make the cut. They didn't get detected as edges, but somebody that annotated this image thought that the edge was important. Okay, so what you see now is that the edges have, quite a bit of green, but there is red there. Okay, and there's not so much blue. Right? So most of the edges are correctly semantically, right? In this case, in this example, it doesn't happen all the time, but in this example, that's how it show up. Okay, and then mostly the failures come from missing edges. Okay. Now, how do we quantify this? Well, we can do this by talking about the recall and the precision of an edge detector. Okay. So what is recall? Recall is, well, we look at the edges that they were in the ground truth, and we count how many of those I actually found with my detector. Okay, so those ground truth, I went looking for edges that should be in the ground truth. How many I found? Did I find 50%, 70%, right? If I find them all, then it's 100%, and that's perfect. So the maximum recall, it's 1, because it's 100%. Okay? So here is the ratio again from the green, which are the correct edges, versus all the edges in the ground truth. That means has the green plus the red. Okay, remember the red were the missing ones. And precision is, of all the ones I detected, how many of this are actually, oh, this is wrong. This should have been blue. So the ones I detected, either right or wrong, how many of them were right? Okay? That's precision. And again, I would like to have 100% precision or a score of 1. Okay? It means that everything that I detected, it was good. All right? So then what you see many times is plots that have the trade-off between precision and recall. Right? And here's recall, here's precision. And this dot over here is measuring the human agreement when they annotated these ground truth images. Like, remember, I said not everybody agrees the same, right? So the precision and recall is not 1-1, okay? But it's close to the top corner that has 100% precision and 100% recall, okay? So this is human performance. Your canny edge detector is this guy over here, okay? And again, keep in mind that the perfect performance will be this corner, right? 100% recall, 100% precision. And the segmentation algorithm that I just described is the black curve, which is here. Okay? So, and again, this was at the time of the publication in 2013. Okay? So they were doing a very decent job, much better than Canny, not yet close to human performance. Okay, we are getting much closer now in the more modern papers of this, even sometimes even better. Okay, questions? Okay, before we move to the next feature, which are corners, let's talk about the project. How many of you read what the project is about? Okay, have you figured out how is relevant while we talk about edge detection and motion segmentation, which is the topic of the project? Yes? What? Can you say?
You're looking at the edges as they change between photo, between frame and image.
Okay, say I have an image of an object. I throw a white car in a black background. Okay. What we have been talking about is edge detection in the spatial domain. So we're looking for boundaries like here that went from dark to bright, or here that went from bright to dark. Okay, so that's in the spatial domain, right? So we talk about doing, for example, one row and finding the first order derivative of the grade level values along that row. Okay, and we saw that, well, if I plotted this row, for example, it will be low because it's black, then it will become white because the car for a period of time, and then it will go back down to black. So I will see something like this, and I'm looking for this guy and this guy, and for doing that I will do the first order derivative of that. Okay? All right, so now what I have is not a picture of the car, but I have a video of the car. Right? That means that now I'm taking multiple, let's assume the camera is fixed, the car is moving in front of the camera, right? And I'm taking multiple images, maybe 30 frames a second or 60 frames a second. Okay? So what's going to happen now? I want to detect that car moving. Okay, the car is moving. And so the way I'm going to do this is, instead of doing derivatives in the spatial domain, what I'm going to do is derivatives on the temporal domain. Why is that? Let's pick this pixel over here. Okay? That pixel right now is black. How about in the next frame? Maybe still black. Now the car is moving, right? So eventually, my car will pass over this pixel. And this pixel will become white. So now what I'm going to be doing is derivatives along this direction at every pixel, right? In each pixel, I'm going to see how that gray level value is changing. If belongs to the background or something that's not moving, you will think that that pixel is not changing intensity. Now, is that right? Is that true? It will be close to, but there's light flicker and there's noise. So that thing is not going to be constant. But if I plot it as a function of time, right, what will happen is that it will be more or less constant. Now the car comes in front. Now it jumps. Okay? So this edge over here tells me that I have motion. Something has happened. Okay? So that's the whole idea. All right? Now, again, images are noisy, so you need to play with noise filtering. Okay? And the project gives you some guidelines of the things I want you to try. So different amount of smoothing, okay? Different type of smoothing, box filter, Gaussian filter, see what works best. Okay? Questions? No? Again, the project, hopefully you have a team. Both members of the team submit in Blackboard the same report. Okay? All right, so let's move now to other features. Okay, so let's first start by defining what I'm going to be talking about, which is corners, okay? And I have this definition that it is where two strong edges meet, okay? That's an intuitive definition of what I think of corners are. Thank you. Yes. Okay. And they can be used for tracking because corners are easy to follow. They could be used for recognition. They can be used for 3D triangulation and in stereo. It can be used for many things. Okay. So here I have an example of a corner. Okay. So this is a cartoon image. We have a darker rectangle and a whiter background, and I'm highlighting in pink and red here one of the corners of this rectangle. Okay, and again, it's a corner because I have a strong edge and a strong edge meeting at one point. Okay, so let me first give you an algorithm of how I'm going to detect that corner. So this is like an oracle came to me and said, do this and you will find corners. Okay, and then we will see why that oracle might have told me that, and if it makes sense, if it works all the time, or do I need to make any adjustments. All right. So here is the oracle. He said, I like to play with matrices, so create this matrix, okay, where it's a 2x2 matrix, okay, and that matrix is defined at every pixel on the image. So for each pixel in the image, I have this 2x2 matrix, okay. This matrix is symmetric, all right, and it's done by taking the output of your favorite edge detection, okay, that estimates the gradient at every pixel. So E sub x over here is the first component of the gradient at that location. E(y) is the second component of the gradient. Okay, so at every pixel in my image, I find my gradient vector, has two components, Ex and Ey. And then what I do is, in a small neighborhood around that pixel, I sum the squares of the first component, and I put that in the element 1, 1. I sum the squares of the second component, and I get the 2, 2 version. And then for the these two guys, I just have the sum of the cross products. Okay? Clear what the algorithm is? Right? So I take my image. At any pixel in the image, I'm going to consider a neighborhood around it. I don't know how big, but it could be 3 by 3, 5 by 5. That's a parameter that I need to figure out. Okay. But at each of these, I'm considering this neighborhood around this guy. At each of these pixels, I know what the gradient was. So I have really, for these two images, one that has Ex, another one that has Ey. Right? This is the first component of the gradient. This is the second component of the gradient at every pixel. Okay. So in this neighborhood, what I do is I take this guy and square it. I take this guy, I square it, and sum over the neighborhood. I sum over the neighborhood, and I also compute the product of the two and sum over the neighborhood. Okay, and that gives me a 2 by 2 matrix. All right? All right, now why is this matrix any good to find corners? Okay, let's say I did this for this, a neighborhood around that corner. How is that matrix going to look like? Let's say this guy over here, all the red points there, right? How does the gradient vector look like? Are both components going to be large? One, only one, right? Which one? Well, again, depends what I call X and Y. But one of them is basically 0 because there is no change along the horizontal direction. And the other one is going to be large because there's a large jump between the top and the bottom. Okay? How about the other side of rectangle? Also, one is 0 and the other not. Are the same ones? Then no, it's the reverse. Right? So what happens to these cross terms? They become 0, right? Because I'm multiplying one that is non-zero with one that's 0. Doesn't matter which one, but in the end I get 0. So, and these guys are going to be fairly large because I'm summing out all the ones that are non-zero in one direction, and these are the ones that are non-zero in the other direction, right? So this matrix looks diagonal. Okay? Something like that. All right? So my friend in the Oracle said, you compute this matrix, and places where I have corners, this matrix is diagonal. So you compute the matrix, you look at it. Is it diagonal? Then I say I have a corner. What happens when I compute this matrix around here, in the middle of the rectangle? What do I get? Zeros, right? What happens if I do it here? Zeros. What happens if I do it far from the corner, if I do it somewhere in the edge here? What does it look like? It is 0? No.
It's going to be all zeros except for x or y.
Right. So one of the elements in the diagonal will be non-zero, but the other one will be 0. So edges will not be diagonal matrices. Okay? So of course, this is a cartoon, right? So when I do this, I'm going to look at the matrix, and it's not going to be diagonal, but let's be optimistic, and it's close to diagonal, meaning that these guys are close to 0, and these are non-zero. And I had to decide, well, are really non-zero or I'm seeing noise? So I had to have a threshold, right? And the threshold says, if the smallest of the elements in the diagonal is large enough, then I have a diagonal, and then I have a corner. End of the algorithm. Do I pay money to my oracle and say, thank you? Am I done? Can I find corners? It seems like a nice algorithm, right? Compute this matrix. It takes some effort, but I know how to do it. I do compute the gradients. I square, multiply, sum, build a 2 by 2 matrix, and then I inspect the diagonal, right? And if elements in the diagonal, the smallest one is actually large enough, then it's not an edge, it's a corner. But if I'm asking this, there must be something more, right? Why I'm not willing to pay yet?
Only detects like right angle.
Right. This is very, very heavily oriented to the orientation of my corner. Okay? So what happens if I have a corner like this? Okay? I like the idea. It worked, right? So let's compute this matrix. I still can do that, right? How is this matrix going to look like? Is it going to be diagonal at the corner? No. Why not? What's the gradient in this, guys? Is it now just one component non-zero and the other one 0? No, that's the problem, right? My edges now have a slope, right? And so both components are non-zero, okay? So when I do this, this guy and this guy, yeah, are the same, but they're non-zero anymore. Okay, so I have a matrix that's not diagonal, but I have a corner. Right? Can I save my algorithm? It seems so promising. What's the problem here? My corner has been rotated, right? If I unrotated the image, then I know how to solve it. How much do I rotate? Well, I need to rotate the orientation of the corner, but I don't know where the corner is, so I cannot know what the rotation is, right? Do you see my dilemma? Okay. Now we're going to see a nice mathematical trick that does that for us. It doesn't need to know what the rotation angle is. It will rotate the amount so that corner becomes vertical or horizontal, and my matrix becomes diagonal. Okay? So then if you think about it, really what I want to do is, well, I have a matrix here that's symmetric. I want to make it diagonal. And I know how to do this in linear algebra. You give me a matrix, I know how to diagonalize it. Okay? This is a symmetric matrix, so I can always diagonalize it. Okay? So what we're going to do is review eigenvectors and eigenvalues. Okay? All right. So let's assume, and this is generic, but it applies to my case, my corner matrix. I have a matrix that's squared. Okay. I have a vector, which is a column vector, and I have lambda, which is a scalar, right? And we say that V is an eigenvector of A with eigenvalue lambda if when I multiply A times V, I get a scale version of V by lambda. Okay? So, and assuming the non-trivial solution, of course. Okay? And so how do we find eigenvalues and eigenvectors? Well, that's easy, right? So here's my matrix A. Okay? Here's an example of an eigenvector and an eigenvalue. How did I find this to show you to you? Well, what we did was solve for this system of equations, right? So I said V has to be an eigenvector, so it has to satisfy that. Then I move this to the other side of the equation, so I get that. Then I factor out to the right V, but I have to be careful in dealing with vectors and matrices, right? So I just cannot leave lambda alone here because lambda is a scalar, and I cannot subtract the scalar from a matrix. MATLAB lets you do that, but really MATLAB is thinking something else, right? So I put here the identity. Okay, so now I have this equation, and now I have a set of linear homogeneous equations where A is known, okay, and lambda is not known, and V is not known, okay, and I want the non-trivial solution for this. And so if I want a non-trivial solution, what happens is that the determinant of the system has to be equal to 0. And that gives me what's called the characteristic equation of the matrix A. Right? The determinant of A minus lambda I equal to 0. That's a polynomial, okay, of degree, the dimension of the matrix, in the variable lambda. And I can set that to 0 and solve for lambda. And that will give me the eigenvalues of the matrix, right? So for this matrix that I have here, which, by the way, in this case is not symmetric, it's just a regular matrix, it's 2 by 2, okay, I compute the determinant of A minus lambda I, right? That gives me a second order equation in lambda, solve for the quadratic roots, right? And I get two values, lambda 1 and lambda 2. Okay, so these are my eigenvalues. How do I find the eigenvectors now that I have my eigenvalues? I plug in lambda in the system of equations and solve for V. Okay, so for lambda equal 1, I get these equations. Of course, they are linearly dependent because the determinant of the system is 0 by design, right? And so of the two equations, really I have only one, and that gives me a vector. Okay, and of course, any scale version of that is also an eigenvector. Typically, we normalize it to norm 1, but okay. And to get the other one, I just plug in the other eigenvalue, and I get that. Okay. Now, there are nice properties that eigenvalues and eigenvectors have. And we are going to use that, actually, to find our corner, so it's worth looking at it. Okay. First of all, if I give you a matrix, square matrix, I define the trace of that matrix as the sum of the diagonal elements. Okay. Now, that number, it's a scalar, is closely related to my eigenvalues. In fact, the trace is equal to the sum of the eigenvalues. Okay? So if I look at this matrix, the trace is 5 minus 2 is 3, and we saw that the eigenvalues were 1 and 2, and when I add up, I get 3. That's not coincidence. That happens all the time. Okay? Now, there's a similar relationship for product. Do you know what the relationship between the eigenvalues, the product of the eigenvalues and the matrix, what is related to? Do you remember? No? Well, it's good I'm reviewing it then. The product of the eigenvalues is equal to the determinant of the matrix. Okay? So again, if you compute the determinant of this matrix, it happens to be 2, which is equal to 1 times 2, which were my eigenvalues. Again, not coincident, that happens all the time. Okay? And it's good, we're going to see in a few slides that we can use this to do corner detection without actually finding the eigenvalues and eigenvectors. We can just have the determinant and we can have the trace and use that to decide whether I have a corner or not. Okay? All right. So some properties. If there is a null eigenvalue, it's an eigenvalue that's equal to 0, that means, of course, that the determinant has to be 0, right? Because the determinant is the product of the eigenvalues. I have an eigenvalue that's 0. That means that matrix is not invertible. Okay. The other thing that's nice is that if you raise to a power the matrix, you have, yes, you have a question? You have the same eigenvectors. Not the same eigenvalues, but the same eigenvectors. The eigenvalues are related by the power. Okay? So if lambda is an eigenvector of A, lambda's eigenvalue of A, lambda square is also an eigenvalue of A square. Okay? But with the same vector V. All right. Now, my C matrix, the corner matrix that my oracle gave me, is a 2x2 matrix, which is nice and small. And second is symmetric. Okay? So now let's look what happens when a matrix is symmetric. Okay, so that means that if I transpose it, I get back the same, right? It's not changed. All right, and let's assume that I have two eigenvectors, Vi and Vj, and the corresponding eigenvalues are lambda I and lambda j. Okay, all right. So since Vi is an eigenvector of A, this must hold, right? If I multiply A by the eigenvector Vi, I get back the same vector scaled by the corresponding eigenvalue. All right? Okay. Now, let's multiply both sides of this equation by the transpose of the other eigenvector. Yeah? Again, you need to check my math whenever I do these things, that the dimensions, for example, are okay, right? I can do this multiplication. All right? So I multiply on both sides, on the left, by Bj transpose. Okay? Now, remember that A is symmetric, right? So let's look at this product over here. Okay? How much is that product? Lambda Vj. Why? Right, so A and A transpose is the same, so I can replace A by A transpose. And I have this, right? And now, since Vj is an eigenvector, right? When I multiply Vj by A, I had to get a copy of that, okay? Scaled by its eigenvalue, okay? And so now I have this guy is lambda Vj transpose. So let's plug that in, and I get this equation. Okay? Yes? So I started by just having two eigenvectors with different eigenvalues. Okay? And just did some algebra, and I got that. Okay? Now, Vj transpose Vi is in both sides. Okay? So let's put everything in one side, factor out Bj transpose Vi, and I have that this equation has to be equal to 0. Okay? Now, if lambda j is different from lambda I, if I have two roots in my characteristic equation, right? If they're distinct, this is not 0, right? This is 0. What does that mean, geometrically speaking? They're orthogonal to each other. Okay? So if I have a symmetric matrix with distinct eigenvalues, the eigenvectors are orthogonal to each other. Okay? All right. Now, let's diagonalize. Okay, so I have a matrix P now that's n by n, So it doesn't have to be 2 by 2. In our case, we're going to be 2 by 2, but in general, n by n. And I have the columns of this matrix. I'm going to call them vector 1, vector 2, vector n. Okay? All right. So now let's take, sorry. And so these are the eigenvectors of my matrix A. Okay, so my matrix A is n by n. I find all my eigenvectors, and I put them in this P matrix, where each column is one of my eigenvectors. Okay? So now I take P, and I multiply it by A. Right? So when I multiply by A on the left, right, this column becomes AB1, and this column becomes AB2, and that column becomes ABN. Right? But these vectors, I made them, they were the eigenvectors. So when I multiply A by V, what I get is lambda times V. Okay? So this is what I get. Right? Okay, so now AP is equal to that. And I can rewrite this as the product of two matrices. The matrix with the eigenvectors and a diagonal matrix with the eigenvalues. Right? So what I'm saying is that A times P is the same as P times this matrix. I call it big lambda, okay, capital lambda, which is diagonal, and it has at the diagonal the eigenvalues. Okay, so now I have AP equal P lambda. P is n by n. I'm going to invert it. Okay, so now I have that P inverse A times P has to be equal to P inverse P lambda, right? And this is the identity, so that means that this over here is diagonal. Okay, so if you give me a matrix A, right, I can convert it to a diagonal matrix that has as diagonal elements the eigenvalues, and the matrix that does that is this matrix that's made out of the eigenvectors. Okay, now what's nice is that if my matrix to start with was symmetric, I show that my eigenvectors were orthogonal to each other, right? And so what happens is that this diagonalization matrix, what it is a rotation matrix. Okay? All right? So I can go from my non-diagonal matrix to the diagonal matrix by applying a rotation, and the rotation is given by the eigenvectors. Okay? So here's an example. This is not symmetric. This is the matrix I showed you earlier. These are the eigenvalues, the eigenvectors. This is the diagonalization matrix. This is its inverse. And you can verify that if you do the product of this, you get the diagonal matrix with the eigenvalues in the diagonal. Okay? Now, if I take a symmetric matrix, and I do that, okay, I find, in this case, the eigenvalues are 16 and 8. These are my unit norm eigenvectors. Okay, this is the diagonalization matrix, which is a rotation of 45 degrees in this case. Okay. All right. So let's go back to images. Only a few minutes, and we pick up on Friday. So I want to apply my Oracle algorithm. Okay. So what we're going to do is we're going to compute this matrix that my Oracle told me, and then I'm going to diagonalize it. Why? Because that's equivalent to rotate it by exactly the amount I would need to make my matrix diagonal, which makes my corner detector work. Okay? So what we're going to do is we're going to have these neighborhoods where I'm computing this matrix. Right? At the center of the neighborhood, I compute the matrix by summing up the squares of the x component, the y component, and the cross products. That gives me a matrix. It's not diagonal. And I can diagonalize it and then look at the eigenvalues, right? And if the smallest eigenvalue is large enough, I got my corner, okay? Now, there are variations that you can do that. I could do it directly sum on the neighborhood, which is equivalent of having a box window. Or I can say, well, I'm doing an average. Let's do a weighted average. And so let's use a Gaussian window. Okay? So now what I have is that I'm going to be looking at how the intensity is changing, okay, in a neighborhood. And I'm going to be doing that as I move in a given direction, okay? And I'm going to do a weighted average of that change in gradient, okay? So here is my cost function. So I have the difference. So I'm computing this around a location, U and V, okay? I'm looking at a neighborhood around U and V, okay? And I'm looking at the intensity in that neighborhood versus the intensity at the center of the pixel, of the neighborhood, okay? And now again, I don't care whether it's brighter or darker. What I really care is that there is an edge. And so I'm doing the square of that difference, okay? So I'm averaging on that neighborhood, okay, in this window, the squares of the differences of the grade level values, okay? Now let's see how this is related to the matrix that my oracle told me about, okay? All right, so let's start by looking at Taylor series expansion, okay? So what I have here is a function of two variables, okay? X and Y, and I'm moving the way, and the place I'm looking at the function a little bit, okay? I move a little bit on the X direction and a little bit on the Y direction, okay? How much? U and V, okay? And so this function, as I move from X, Y a little bit, right, can be approximated using Taylor as the value at X and Y, right, plus the gradient in the X direction multiplied by how much I move in the X direction, plus the gradient in the Y direction multiplied by how much I move in the Y direction, plus higher order terms, okay? So that's a first order approximation of a two-dimensional function evaluated at X, Y, and when I move a little bit, okay, in the X and Y direction, I move U in one direction and V in the other one, okay? All right, so now let's use that in my cost function. And for now, to simplify things, I put W equal to 1, okay? So I'm doing the box filter, all right? So I have this square, the sum of the squares differences. And so let's expand this guy using Taylor, right? So what I get is that this guy is the intensity at xy plus u times the gradient in the x direction plus v times y in the y direction minus this guy, and all of that is square, right? Now this term and this term cancel, yes? So I'm left with this sum over here, right? And I hope it's starting to look similar to my matrix, right? Because now I have the sum of the square of the gradients in one direction, the sum of the square of the gradients in the other direction, and the sum of the cross products actually twice. Okay? All right. So let's write that down in matrix format. Okay? This is a scalar, by the way, right? It's just one sum, okay, of values. But I can always write it this as a matrix equation, right? A quadratic form, where I have the vector u and v as a row on the left, the vector u and v as a column on the right, and in the middle I have, that's my corner matrix, right? I changed notation, sorry. Before I call it E, now I call it I, but it's the same thing, okay? So I put back the sum in, so these are not changing, right? And so what I have over here is my corner matrix, all right? So this is a different interpretation of why my oracle friend might have suggested that matrix to work with, right? What we was looking was, how are the gradients changing in that neighborhood in a way that I see whether there's a corner or not, okay? So if you look at this quadratic form, okay, remember I dropped the W, I can put it back. Really what it does is change the matrix with W in front, okay? So what we're going to do on Friday, we're going to see how I use this to actually find corners, okay? Do I really need to do a diagonalization of this matrix, or I can get by without not doing that, okay? And after that, we're going to move on to other more higher level features like lines. So we're going to talk about the half transform, okay, and boundaries, all right? Okay, see you on Friday. And again, if you need to talk to me today, my office hours will be at the lab in Hayden 13. It's in the basement of Hayden, on the tunnels.